Section 4.2, Homogeneous Linear Equation, second order ODE. In order to solve these kind of equations, first we have to define some concepts, one of which happens to be linear combination of two functions. Definition is, given two functions, okay, so given two functions, namely f of x and g of x, if there exist constants like c1, c2, where we can form this expression, c1 of f of x and c2 times g of x, then we call the expression 1, c1 f of x plus c2 g of x, as a linear combination of what? F of x and g of x. For example, if I have, let's say, two functions, let's say e to the x, and g of x is, let's say, x squared plus 1, linear combination of f of x and g of x happens to be c1 e to the x plus c2 x squared plus 1, where c1 and c2 are scalars, meaning they're real numbers, correct? So that's basically what linear combination is. One more example, suppose I have, let's say, I don't know, vector v, okay, which is, let's say, 2, -3, and vector w, which is like 0, 5. The linear combination of these vectors will be c1v plus c2w. Once again, c1 and c2 are scalars. So that's basically what we mean by linear combination. The next concept is called linearly independency. So what is linearly independency of two functions? Definition: two functions are said to be linearly independent, so this would be independent, if the ratio of the functions is not a constant number, so k is constant. Otherwise, the functions are called linearly dependent. So once again, if you form the ratio of two functions, and the ratio is not a number, is not a constant, then we say that functions are linearly independent. Otherwise, if it comes up as a function, as a constant, then they are linearly dependent. For example, suppose I have f of x is equal to e to the 2x, and g of x is equal to e to the 3x. If I form the ratio of these two functions, it doesn't matter what goes on top, what goes at the bottom, e to the 2x divided by e to the 3x is e to the -x, and that's not a constant. Therefore, conclusion is what? E to the, 2x and e to the 3x are linearly independent. In a layman's term, that means they cannot be combined. On the other hand, if I have, let's say, I don't know, f of x is equal to, let's say, e to the 2x, and g of x is equal to -6 e to the 2x. So if I form the ratio of these two functions, I get e to the 2x over -6 e to the 2x, and that's -1/6, which is a constant. So the conclusion is e to the 2x and -6 e to the 2x are linearly dependent functions. So dependent. So these guys were linearly independent, these guys were linearly dependent. Finally, what we have is called fundamental solutions for a second order differential equation, homogeneous kind, where you have constant coefficients a, b, c. Remember, in this case, a, b, c are constants, correct? So given the ODE, which is once again called second order homogeneous linear differential equation with constant coefficients. If you got like y1 and y2 as its solution, then for these solutions, these two solutions, notice I have two solutions because it's a second order, they are said to be fundamental solutions if they satisfy three conditions, correct? You can't just take any old solution and call it fundamental. They have to satisfy these, what, three conditions. Each of these functions have to satisfy the differential equation. So that's number one. Both of the functions have to be linearly independent, meaning they cannot be combinable, okay? And the number of solutions has to be the same as the order of differential equation. If the order, like in this case, is 2, I need 2 solutions, correct? So that's basically those fundamental definitions. So with that, so now we can go over this next topic, which is given two solutions, given these two functions, if they happen to be fundamental solutions to a differential equation, a y double prime plus by prime plus cy equals 0, any linear combination of these two fundamental solutions is also a solution to our differential equation. In other words, if these two guys satisfy the three conditions of what? Fundamental solutions, then linear combination of those guys happens to be also a solution. Okay, let's see what that means. Suppose you are given this differential equation, which is second order linear homogeneous with constant coefficients, correct? Imagine I tell you, or they give us sine of x and cosine of x as two solutions for this differential equation. The question is, are these fundamental solutions? Well, in order to check to see if y1 and y2 are fundamental solutions of what? Y double prime plus y equals 0. Remember, I have to satisfy three conditions. What are they? First condition is each of these guys have to satisfy the differential equation. So I need to take the derivative of this guy twice. So that's cosine of x. One more time. That's minus sine of x. Now substitute here. So minus sine of x plus sine of x equals 0. It checks. Next, y2 is equal to cosine of x. Take two derivatives. This is minus sine of x. One more time, right? So you get minus cosine of x. Substitute these guys in the original differential equation. And lo and behold, what? This guy is also 0. So it's satisfied. So that's condition 1. Condition 2, if I take the ratio of sine over cosine, I get tangent. Tangent is not constant, is it? So therefore, cosine and sine happens to be linearly independent. Linearly independent functions, correct? So they are not combinable. The third condition is what? The number of the solutions I was given matches the order of the differential equation. I was given two functions and what? That kind of matches the order. So condition number 3 is satisfied. So I can call what? Sine of x and cosine of x as a fundamental solution of this differential equation. However, based on this theorem, if two functions happens to be fundamental solution of a differential equation, any linear combination of those guys is also a what? A solution. What does that mean? That means if I take linear combination of sine and cosine, which is what? C1 sine of x plus C2 cosine of x, I can show you this guy is also the what? Solution of what? Y double prime plus y equals 0 for any constants C1 and C2, correct? So let's take two derivatives. So this would be c1 cosine of x minus c2 sine of x. One more derivative. That would be minus c1 sine of x minus c2 cosine of x. Substitute these guys into what? Into original differential equation. So you get what? Y double prime, which is minus c1, what is it? Sine of x, correct? Minus c2 cosine of x plus y, which is c1 sine of x plus c2 cosine of x. Is that equal to 0? Yes, it is. These guys cancel, so does those guys, so it checks. So the takeaway from this theorem is what? If you have your hands on, if you get your hands on fundamental solutions, y1, y2, and you check and see there are fundamental solutions, then any linear combination of those guys happens to be fundamental solutions as well. The solution of a differential equation as well. The next item we'd like to go over is called auxiliary polynomial, which is denoted by P of R. And the roots of this auxiliary polynomial, what? Kind of enables us to find the solution for these second-order homogeneous differential equations with constant coefficients. The idea is this. If you have, let's say, let's say A y double prime plus b y prime plus cy is equal to 0, the claim is what? The solution for these kind of equation looks like this. E to the power of rx, where r is any real number. So this is basically the looks of what? Solution to homogeneous linear differential equation, whether it's order 2 or higher order. This is how it looks like. It's always an exponential function, e to the power of rx. R is any real number. So if I take the derivative of this, so that's r e to the rx, one more derivative, that's r squared e to the rx. If I substitute these guys in the original differential equation, I get a r squared e to the rx plus b r e to the rx plus c e to the rx equals 0. So now I'm going to factor out e to the rx, and I'm going to come up with ar squared plus br plus c is equal to 0. So you and I, we both know e to the rx, no matter what x is not going to be equal to 0. So the idea is ar squared plus br plus c has to be equal to 0. And remember, r is a real number. So if you use quadratic formula, r is equal to what? Minus b plus or minus square root of b squared minus 4ac over 2. When you solve this quadratic formula, when you solve this quadratic equation for r, there are three possible answers. Either you get two distinct real roots, or you get repeated roots, or you get complex roots. So either the roots will be R1, R2, which means distinct, or they will be repeated R1, R1 twice, or they will be complex, like let's say, they would be like R is equal to, let's say, A plus or minus BI. Okay, so that would be like R equals. In other words, you would have a complex solutions, correct? So complex means you would have what? I in your final answer, correct? Remember what I was from algebra classes is square root of -1, which is imaginary number, correct? So in this case, we like to explore what? These two cases, namely if the roots of this so-called auxiliary polynomial, when we set it equal to 0, we get what? Distinct roots or repeated roots. How would the general solution for this kind of differential equation look like? Okay, so let's see now. So we established the fact that what solutions to that kind of differential equations would have this kind of form, e to the power of rx. And now let me show you how to solve these kind of equations from scratch. So here's what we do. We go, okay, first step one is form what? The auxiliary polynomial function, correct? P of r. How do you do that? Well, replace the y double prime with r squared, y prime with r, and then this guy is just constant. Where did this guy come from? Remember, if you kind of like substitute this general equation, e to the power of rx, factor out what? E to the power of rx from the result, you will end up with what? That polynomial, correct? And basically, that's where it came from. So what I did, I kind of claimed, the claim was e to the rx is the solution. So I took like two derivatives of this and substitute here. Then I factored out e to the rx, and this is what's left of it, okay? In other words, y prime is r e to the rx, okay? And y double prime is what? R square e to the rx, correct? So if I substitute those guys here, I get what? R square e to the rx minus what? R e to the rx minus 6 e to the rx equals 0. Factor out what? E to the rx, lo and behold, you get r squared minus what? R minus 6 equals 0. But you and I, we both know, just like before, e to the rx cannot be 0, so it has to, this guy has to be 0, and that's where it comes from. Set this equal to 0 so you can find the roots of this so-called auxiliary polynomial. So that's what it's called, auxiliary polynomial. Okay, I'm going to factor this guy out because it's a quadratic equation. If you can factor it, so please factor it. Do not use quadratic formulas. Sometimes students use quadratic formulas, still they don't come up with the right answer. So if you can factor it, factoring is easier. So let's see now, what do we have? We got like -3 plus 2. Set these guys equal to 0. Guess what you get? You get two distinct, meaning different, what? Roots, real roots. So the fundamental solutions happens to be what? E to the power of 3x and e to the power of -2x. You can check and see these are fundamental solutions. Each of these guys satisfy the equation. They are linearly independent, and the number of solutions I have matches the order of differential equation, which is 2, and I have 2 functions. So any linear combination of this would be the general solution for this equation. So I'm going to take the linear combination, c1 e to the 3x plus c2 e to the -2x, and what do you know? I have my general solution, and that's pretty much the end of that problem. So when they say solve, they mean find this y. Remember, finding the fundamental solution is not enough. I need to take the linear combination of these guys and let people know, regardless of what C1 and C2 is, okay, whatever you choose for C1, C2, the result, y equals whatever C1, C2 is, still satisfies this equation. So that's why this is called general equation. Sometimes they want you to solve the equation subject to some initial conditions. When they give you initial conditions, incidentally, the number of conditions also depends on the order. That means they want you to find C1, C2, correct? So we decided the general solution is C1 e to the 3x, C2 e to the -2x. So now I'm going to impose the first condition, which is y of 0 equals 1. What does that mean? That means when y is 1, x is 0. So I get C1 plus C2. Keep in mind, e to the power of 0 is 1, right? So that's one equation right there. The next guy is y prime of 0 is -1. So I have to take the derivative of my general solution, which is what? 3c1 e to the power of 3x minus 2c2 e to the power of -2x, correct? Now I'm going to impose this condition. Y prime of 0 is -1. So that means y prime is -1 when x's are 0. So I'm going to get 3c1 minus 2c2, correct? And this is my what? Second equation. Now I'm going to form what? This system of equation, linear equation, like so. Okay. And I'm going to try to solve this system of linear equation for C1, C2. One way to solve this is what? Multiply perhaps the top equation by, let's say, 2. So you get 2c1 plus 2c2 is equal to what? 2. And then 3c1 minus 2c2 equals -1. These guys cancel. So you get 5c1 equals what? 1, is it? So c1 is equal to 1/5. Now that you know what c1 is, go back to either of these equations, find what? c2. So I know from first equation, c1 plus c2 is 1. I just found out c1 is what? 1/5. So c2 has to be 1 minus 1/5, which is what? 4/5, is it? So the particular solution is what? Is 1/5 e to the power of 3x plus 4/5 what? E to the power of -2x. So this, we call it what? Particular solution. Particular solution. So particular means what? One of a kind, meaning it's a specific solution which satisfies these initial conditions. So in your particular solution, there should be no C's. Do you see it? That would take care of distinct roots. Sometimes you have what? Repeated roots. Here is a fact. If you have, let's say, you set the auxiliary polynomial equal to 0 and you get like R1, but R1 was multiplicity 2. Multiplicity 2 means what? You get R1 twice. Unfortunately, the answer is not e to the R1x and e to the R1x, because then they would be linearly dependent. One of the conditions of fundamental solution is what? The function has to be linearly independent. So it turns out one of them, the first one is e to the R1x, but the second one is not e to the R1x, is x times e to the R1x. And that's true in general. That means if you have a repeated root m as in Mary times, then the fundamental solutions are e to the R1x, x times e to the R1x, x squared e to the R1x, all the way to x to the power of m minus 1 e to the R1x. So in this particular question, problem, auxiliary polynomial is r squared plus 4r plus 4, so that there goes my auxiliary polynomial. Notice, just by inspection, I can write the auxiliary polynomial. Pretend you're replacing what? Y double prime with r squared, y prime with what? R, and the y with 1, constant, 1. So if I set P of r equal to 0, so I get r squared plus 4r plus 4 is equal to 0, which means r plus 2 squared equals 0, which means r is equal to -2 with multiplicity 2. What is multiplicity 2? That means I have what? -2 twice, because this guy is r plus 2 times r plus 2 equals 0. So r is equal to -2 twice, because the degree of the polynomial is 2, so I gotta have 2 answers, correct? However, the fundamental solution is not e to the -2x and e to the -2x twice. One of them is e to the negative 2x. The other guy is x e to the negative 2x. But we are not off the hook yet. Now the general solution is a linear combination of these guys. So you go c1 e to the negative 2x plus c2x e to the negative 2x. Now you have the final answer. Do you see it? And this is what we know as general solution. So when they say solve here, that means find this expression, correct? So once you find the fundamental solutions, don't forget to take the linear combination of those functions and set it equal to y. Now this is the solution to that differential equation. Sometimes the order of differential equation exceeds 2, which is okay, you know, that's fine. For instance, you have y triple prime plus y double prime minus 2y prime equals 0, correct? So auxiliary polynomial is r cubed plus r squared minus 2r is equal to 0. Remember, r triple prime gets to be replaced with r cubed, y double prime with r squared, and y prime with r, and there's no y, so I don't have to worry about it. However, if I set the auxiliary polynomial equal to 0 to find the roots, so that's like setting r cubed plus r squared minus 2r equal to 0. And if you factor out an r, you get r squared plus r minus 2 is equal to 0. You see it. So now either r is equal to 0 or r squared plus r minus 2 is equal to 0. So the degree of the polynomial is 3, so I expect to come up with 3 answers. Here's one of them. The other 2 has to come up with this quadratic equation. So factor this out, r, let's say, I don't know, 2 plus minus. So r is equal to negative 2 or positive 1. Do you see it? So the fundamental solutions are e to the 0x, e to the negative 2x, e to the 1x. Correct? Remember, the number of solutions should match the order of differential equation. And these 3 functions are linearly independent. However, to prove these guys are linearly independent, I cannot take the ratio of these guys 2 at a time. I have a different test, which I will go over that in the next section. When the number of solution exceeds 2, to prove these are linearly dependent or independent, I repeat, I cannot take the ratio of these guys 2 at a time. I have a test called Wronskian test, and I will go over that in my next video. So for now, this would be 1, because e to the 0 is 1, e to the negative 2x, e to the x. So any linear combination of these guys, like c1 times 1, c2 times e to the negative 2x, and c3 e to the x should do the job. There it is. So this is, once again, my general solution. Why do we call this general solution? Because we have constants, correct? And notice the number of constants also matches the order of differential equation. So the differential equation was 3rd order. This is called 3rd order homogeneous linear differential equation with constant coefficients. And notice my C's, I have 3 C's. Also, I have 3 solutions. So finally, this guy right here, the question is solved. This is a 3rd order homogeneous. Homogeneous because you have a 0 on the right side. If you don't have a 0, then those would be called non-homogeneous. Those are a little bit trickier. So we'll go over those in perhaps a couple of sections from this section. Okay, so these are easy to solve because they're homogeneous and you have constant coefficients and the equation is linear. So immediately write the auxiliary polynomial by inspection. So that will be r cubed minus 2r squared minus 4r. And now you have a y component, so plus 8 is equal to 0. So notice what I did. I replaced the y triple derivative with r cubed, y double prime with r squared, y prime with r, and this guy is just a constant, 8. How did you get this? Remember, the claim was the solution is in this form. So when you take 3 derivative of this guy and substitute right here, factor out e to the rx, this is the polynomial you're going to end up with. In algebra classes, so I'm going to set this guy equal to 0 to find the roots of this polynomial. So that would be r cubed minus 2r squared minus 4r plus 8 is equal to 0. So this is a 3rd degree polynomial function. To factor this polynomial, notice this is a 4-term polynomial. If you remember from algebra classes, you factor these guys, 2 at a time. So you group them 2 at a time. From the first 2, you factor out r squared, so you get r minus 2. From the last 2, factor out -4, you still get r minus 2. But from these 2 guys, these 2 terms, you factor out r minus 2, you get r squared minus 4 is equal to 0. But this guy is a difference of 2 squares, so that factors as r minus 2, r plus 2. So therefore, the roots are r is equal to 2 with multiplicity 2. Notice these guys give you the same roots. And then r is equal to what? -2 multiplicity 1. So you have a repeated roots here, folks. R minus 2 is what? Is equal to 2 twice. Once for this parentheses, one for that guy. So it's multiplicity 2. So what does that mean? That means when it comes to 2, the solutions are e to the 2x and x e to the 2x, because these are repeated. But when it comes to -2, that's not repeated, so that's just e to the -2x. Once again, what do I have? 3 functions. You can check and see there what they check the conditions of fundamental solutions. But to show these are linearly independent, stay tuned for next video when I show you how to prove what? When you have more than 2 functions, they are linearly independent or not. But take my word for it, they are linearly independent. But that's not it. We are not off the hook. Now I have to take linear combination of these and set it equal to y. So the final answer is c1 e to the 2x, c2x e to the 2x, and c3 e to the -2x. And folks, we got our general solution. So this is general solution. Once again, notice it was a 3rd order differential equation. And notice I have 3 linearly independent constants, as well as 3 linearly independent what? Functions. In other words, I can combine the c's, and I can combine these functions. So this is the final answer for this 3rd order linear homogeneous differential equation with constant coefficients. Thank you.